In this section, we'll learn about relevant aspects of the engine. This course includes 11 sub-sections: types of engines, 4-stroke cycle engine operation, engine specifications, combustion of petrol engines, diesel engines, components, fuel and intake, petrol engines, fuel and intake, diesel engines, emission control systems, cooling and lubrication systems, and engine electrical systems. These topics will be introduced in 2 parts. First of all, let's learn about the types of engines and the way they are classified. The engine is a power unit of the vehicle for converting fuel energy into mechanical energy. For instance, in petrol engines, a mixture of gasoline and air is introduced into the combustion chamber, and then it is compressed and ignited to produce thermal energy with high temperature and high pressure. The thermal energy thus produced is exerted to the piston for conversion into mechanical energy of motion. This type of engine is called an internal combustion engine. There are 3 ways to classify engines. In accordance with the stroke principles, engines can be divided into 4-stroke cycle engines and 2-stroke cycle engines. In accordance with the manners of combustion, engines can be divided into spark ignition engines, i.e. petrol engines, and compression ignition engines, i.e. diesel engines. And, in accordance with the cylinder arrangement, engines can be divided into inline engines, B-type engines, horizontally opposed type engines, and horizontally mounted type engines. 4-stroke cycle engines are widely used. We will study their operation in detail in the next subsection, so let us skip it for now. 2-stroke cycle engines are generally used for motorcycles, and they operate like this: 1 cycle of operation, scavenging, compression, combustion, and exhaust is performed while the piston makes 2 strokes, 360 of operation. Accordingly, a mixture of fresh air and fuel is sucked into the crankcase during the compression stroke of the piston, and the mixture of air and fuel already compressed in the crankcase by the downward movement of the piston enters the cylinder through the bypass passage, and replaces the burnt gases in the cylinder. The operation of petrol engines and diesel engines will also be described in details in the sub-sections that follow. Let us look at different engine cylinder structures. This is the cylinder arrangement of inline type engines. This is the cylinder arrangement of V-type engines. This is the cylinder arrangement of horizontally opposed type engines. And this is the cylinder arrangement of horizontally mounted type engines. Next, we'll learn about the operation of 4-stroke cycle engines. Please note the running mode of 4-stroke cycle engine in the figure. Its 4 strokes are intake stroke, compression stroke, combustion stroke, and exhaust stroke. To move to the next slide, please click on Next button. When the piston moves down with the intake valve open, the air-fuel mixture is sucked into the cylinder. This is the intake stroke. To move to the next slide, please click on Next button. After the intake stroke is complete, both the intake valve and exhaust valve are closed, and the air-fuel mixture in the cylinder is compressed as the piston moves up. This is the compression stroke. To move to the next slide, please click on Next button. After the compression stroke is complete, the compressed air-fuel mixture explodes as it is ignited by an electrical spark produced by the spark plug. The pressure of the hot and burnt gas pushes the piston down to turn the crankshaft. This is the combustion stroke. To move to the next slide, please click on Next button. After the combustion stroke is complete, as the piston moves upward, the burnt gas is exhausted from the exhaust valve to start the exhaust stroke. One cycle of operation ends when the piston reaches the TDC position. To move to the next slide, please click on Next button. In this section, we will learn about engine specifications and relevant aspects. We will learn about engine specifications, bore and stroke, engine displacement, compression ratio, engine performance curve, and other professional knowledge. You will also see two new words, TDC and BDC. TDC, when the piston is at the uppermost position of the cylinder. BDC, when the piston is at the lowermost position of the cylinder. To start, let's learn about several parameters and their calculation associated with engine displacement. First, engine displacement is calculated using the formula below. Engine displacement is equal to volume of cylinder multiplied by number of cylinders. Second, the volume of a cylinder is calculated using the formula below. Volume of cylinder is equal to cylinder area multiplied by stroke. Third, the area of a cylinder is calculated using the formula below. Cylinder area is equal to pi divided by 4 multiplied by square of cylinder diameter. Therefore, the formula for engine displacement is pi divided by 4 multiplied by square of cylinder diameter multiplied by stroke multiplied by number of cylinders. Now, let's learn about the concepts and formulas of the compression ratio. The compression ratio indicates how much intake air or mixture air is compressed. Generally, it is 8:1 to 12:1 for a petrol engine, and 15:1 to 22:1 for a diesel engine. The calculation formula is volume of combustion chamber plus volume of cylinder divided by volume of combustion chamber. The engine performance curve diagram can reflect the performance parameters of the engine. The engine performance curves show the engine output kilowatt and engine torque Newton meter at the respective numbers of revolution during full load operations. In the engine performance curve diagram, the horizontal axis shows the engine speed and the vertical axis shows the corresponding engine output and engine torque. The engine's performance is as shown in the figure. The maximum output is approximately 165 kilowatt, and the maximum torque is approximately 275 Newton meter. In this section, we will learn about combustion of petrol engines. In this section, we will first learn about the air-fuel mixture and irregular phenomena in combustion. An improper air-fuel mixture may not only cause reduced engine power or deterioration in fuel efficiency, but may also damage the engine. To move to the next slide, please click on Next button. A certain ratio of air and fuel is necessary for appropriate combustion. This is called the air-fuel mixture ratio and is represented by weight percentage, not volume percentage. Theoretically, complete combustion of 1 gram of fuel requires 14.7 gram of air, in which case the air-fuel ratio is referred to as the ideal air-fuel ratio. If the fuel content is greater than the ideal air-fuel ratio, a rich mixture will be produced. In general, the engine requires a rich mixture when it is started or accelerated. If the fuel content is less than the ideal air-fuel ratio, a lean mixture will be produced. In general, the engine requires a lean mixture when it is decelerated. Petrol engines will sometimes experience irregular combustion, such as knocking. This is a common phenomenon in irregular combustion. When an excessive load is applied to a petrol engine, the engine sometimes produces a noise that sounds as if someone is tapping on the cylinder wall with a light hammer. To eliminate this phenomenon, the following common measures should be taken. 1. Remove carbon sludge accumulated in the combustion chamber to reduce the compression ratio. 2. Use gasoline with a high octane rating. 3. Adjust the ignition timing to retard the ignition timing. It should be noted that carbon sludge increases the compression ratio and the temperature during engine operation. Also, carbon sludge can ignite the gas before the spark plug sparks. This makes a knocking sound, so the carbon sludge must be removed in time. Petrol engines will have other irregular combustion phenomena such as these. After fire, after burn, an explosion or self-ignition occurring in the muffler. This occurs when unburned fuel and the exhaust gas explodes from contact with the fresh air. Backfire, combustion which is carried back into the intake system. This occurs when the ignition timing is poorly adjusted. Run-on, a condition in which an engine continues to fire after the ignition switch has been turned off. Also called dieseling. This phenomenon of run-on occurs when the ignition timing is not set correctly, or when the engine is overheated. In this section, we will learn about diesel engines. In diesel engines, air is heated by compression and a charge of vaporized fuel is injected into the combustion chamber, causing self-ignition due to the compression heat of air. The output power is controlled by the amount of fuel injected. The structure and the operation mode of diesel engines are quite different from those of petrol engines. This comparison chart shows that its compression ratio and compression pressure are higher than those of petrol engines, and that it has different output control and ignition methods from petrol engines, and greater noise and vibration than petrol engines. Comparing the four-stroke process, we can intuitively understand the different operations of diesel engines and petrol engines. In the intake stroke, the petrol engine draws a mixture of air and fuel into the cylinder. But in diesel engines, air alone enters the cylinder. In the compression stroke, in diesel engines, the heat of the compressed air ignites the fuel. So the air must be compressed in such a way that its temperature reaches the ignition temperature of the fuel. Generally, this temperature is 400 to 500 degrees Celsius. In diesel engines, the compression ratio is 2 or 3 times as high as in petrol engines. In the combustion stroke, the ignition method of diesel engines is different from that of petrol engines. The petrol engine uses spark plugs to electrically ignite the air-fuel mixture. In diesel engines, however, the fuel is injected into the combustion chamber from the injection nozzle at the end of the compression stroke. The high temperature of the compressed air spontaneously ignites the injected fuel. In the exhaust stroke, the gas after combustion in diesel engines is then exhausted through the exhaust valve. High-pressure common rail injection is a more advanced diesel engine system used to address increasingly stringent emissions regulations. It is a structure completely different from that of traditional distributor-type injection pumps. High-pressure common rail fuel systems include a fuel supply pump, a common rail, fuel injectors, engine state detecting sensors and ECU to control these components. Now, let's learn about engine components. In this section, we will learn about the major components of an engine, how they work, their purpose and structure. Cylinder blocks are an important component of engines. The figure on the left shows an example of a four-stroke cycle. 4-cylinder inline, overhead camshaft engine. All of the engine components are attached to the cylinder block. The cylinder head is mounted on the upper surface of the cylinder block, and together with the piston, it forms the combustion chamber. The figure on the right shows the mounting position of the cylinder head. The cylinder head structure varies depending on the shape of the combustion chamber, camshaft location, valve mechanism, etc. Next, let's look at the piston. Pistons are composed of a piston head, a piston skirt, a piston pin, a piston wall and other components. The piston head diameter is smaller than the piston skirt diameter. This is because the piston head is directly exposed to the extremely high temperature of combustion, and its diameter becomes larger due to the heat expansion. Also, the piston wall in the piston pin direction is thicker than that in the thrust direction. For this reason, the heat expansion of the piston is larger in the piston pin direction. To compensate for this, the piston is designed in an oval shape with smaller diameter in the piston pin direction. This video shows how the piston is expanded. After watching this, you can intuitively understand pistons. To move to the next slide, please click on Next button. There must be a slight clearance between the piston and the cylinder wall, so compression rings are necessary, as shown in the left figure, to prevent leakage during the up and down motions of the piston. Another important function for these piston rings is to cool the piston by conducting heat to the cylinder wall. The oil rings shown in the right figure serve to control lubricating oil on the cylinder wall so as to enable the cylinder wall to maintain the proper oil film thickness. Now let's learn about the crankshaft. The deep blue area in the left figure is called the crank journal. The crank journal is supported on the cylinder block by means of a bearing. The pale blue area, called the crank pin, is attached to a connecting rod of the crankshaft. Looking at the right figure, the bearings of the crank journal are lubricated with the pressurized engine oil supplied through the oil gallery of the cylinder block. This oil also provides lubrication to the bearings of the crank pin through the oil hole in the crankshaft. Now let's learn about camshaft. A camshaft has a series of cams arranged for opening and closing the intake and exhaust valves. In a 4-stroke cycle engine, the camshaft rotates at half speed of the crankshaft. The camshaft location in the engine is often used to indicate the type of the engine. If, for example, the camshaft is mounted at the top of the engine, the camshaft is called the overhead camshaft, or OHC. The OHC engine with one camshaft in cylinder head is called single overhead camshaft engine, or SOHC, as shown on the left. If there are two camshafts, the engine is called double overhead camshaft, or DOHC, as shown on the right. Next, let's learn about the relevant aspects of the valve. The figure on the left shows the valve timing. Each valve, intake and exhaust, is opened and closed as the engine camshaft rotates, and the camshaft is driven through the timing belt or chain by the crankshaft, which is called the valve timing. The figure on the right shows the valve spring, which exerts pressure in the valve closing direction to maintain air tightness for preventing leakage of gas for the valve. Variable pitch and double springs are introduced to prevent the occurrence of valve surging. Thank you.